All right, let's talk about conjugate addition in alpha, beta, unsaturated ketones and aldehydes, and a little bit about carboxylic acid derivatives at the end here. So situations where that 1,4 conjugate addition is preferred. So if we look, there are two scenarios we might run into. The first is if we have an anionic nucleophile. And so in that case, and we add, and again, the difference between a 1,2 and a 1,4 product, we label the alpha beta system 1 to 4, and whether the nucleophile attacks the 2 position, like we talked about in our other lesson, or it attacks the 4 position here first, determines the outcome, the product of the reaction. So again, we're focusing on scenarios where the 1,4 addition product is going to be our major product, our focus of this lesson. All right, so again, with an anionic nucleophile, what we're going to see, and I'm going to redraw it over here, we're going to see this attack here occur at the 4 position, kick over the pi bond, and kick up our oxygen to a negative charge. Our pi bond goes up to a negative charge on our carbonyl position. What this does is it creates the backbone here of our 1,4 addition product, but we've now got an enolate. Okay, at this point, the enolate, if there's proton available, can tautomerize, or we can bring the pH down just enough to neutralize, and if we do that, we can show this as a hydronium ion in step 2 is available, and so that enolate tautomerizes directly back to the ketone here, creating our 1,4 conjugate addition product here. Okay, so our mechanism for anionic nucleophiles is going to follow this particular method of procedure for the mechanism. All right, we may need an acidic step there to work up the reaction. If we have a neutral nucleophile, then we are looking at a slightly different mechanism because the nucleophile provides its own proton for capping off the product at the end. Again, some 1,2 product may be formed. We're focusing on when this 1,4 addition is the major product. And so we can take our nucleophile, attack position 4. This is also called beta addition because the alpha and beta carbons can be labeled 1 carbon and 2 carbons away from the carbonyl there respectively. So we could call it that as well, beta addition, conjugate addition, or 1,4 addition. When that attack occurs, we kick over and kick up to an enolate yet again. In some cases, you may have already protonated the carbonyl if there's acid present at the beginning, but in the case of sulfides or amines, we might have a good enough nucleophile to add directly here without needing any acidic activation. Just depends on the reaction. But if we attack here, count your carbons, 1, 2, 3, 4, 1, 2, 3, 4. We've got an extra carbon there. Let me get rid of that. And there's our nucleophile that has just added, and it's got an extra proton. Okay, so what we can do is we can show a base from solution, removing that extra proton from the nucleophile. Our enolate's still hanging out here, and then we can show that protonated base from solution, just like we did before with the acidic proton of hydronium, but we've already got one here. We can tautomerize directly back to the ketone. And there's our 1,4 conjugate addition product. Okay, so we'll see examples of both here. Could see examples of both because there's anionic bases that are weak. There are neutral bases that are weak. And so let's carefully define when conjugate addition is going to be favored for alpha, beta, unsaturated ketones and aldehydes specifically here. And that's when we have soft nucleophiles. So We define those as a good nucleophile and a weak base. This is exactly the same as we would have defined it when we were talking about substitution elimination reactions. Good nucleophile, we learned a list of them. We've got them repeated here and labeled right below us here, part A. Weak bases means that their pKa, so if this is the acid, the pK or the base form, the pKa of the conjugate acid, whether it's protonated with a plus formal charge or neutral, doesn't matter. Each acid's listed in a table with its conjugate acid pKa there. And we want that pKa to be less than 15, more acidic than acid with a pKa of 15, in order to reduce the conjugate base strength to a point where it's not going to be seeking that 1,2 position as strongly. So weaker base goes for the less polar position. That's the soft nucleophile, prefers the softer charge position of the alpha beta system that we have here. Either call it alpha beta or call it the 1, 2, 3, 4 position as we attack. Okay, and if we do attack that beta position with a cyanide ion, just like our mechanism for the formation of a cyanohydrin, we would want to use excess cyanide ion and HCl in order to prevent reversal kicking off of the cyanide ion. Ultimately here, our product is the beta substituted ketone. Okay, so a remote functional group. It's a very powerful reaction. So we just looked at a nitrile. Before we move off the screen here, Gilman reagents are not nearly as polar as organolithiums and Grignards, so they tend to add beta. Some enolates. So we looked in the other lesson at hard nucleophile enolates. Some of those add beta. It's just hard to predict with the harder enolates, the more basic conjugate bases of the functional groups, to whether they're going to add 1, 2, or 1, 4. But these enolates, the beta difunctionalized enolates, so we'll have the functional group, the carbonyl. Okay, so any one of our beta diketones, dialdehydes, diesters, nitrile, there's a whole bunch of them. And these bases are stabilized in 3 ways. We'll look at a resonance contributor, a hybrid of all 3 in just a moment. And so they are very soft nucleophiles. They strongly prefer the beta position. So we do have a high degree of control with those nucleophiles. Amines in their neutral form, primary or secondary. Okay, so we can do primary or secondary amines. Sulfides in their neutral form or their anionic form, either one, are weak bases and good nucleophiles. The cyanide ion we just looked at, carboxylates. Okay, so we can add carboxylates. Potentially, some oxygen nucleophiles are a little more finicky with these reactions. They tend to be highly reversible, so there are conditions typically in actual preps that you have to be careful with. Halides can also add in the appropriate solvents when they are good nucleophiles. Okay, so protic solvents can tend to push those halides into good beta nucleophiles. All right, so there are good nucleophiles, weak bases, just like we saw them with substitution elimination. Looked at the cyanide ion, the amine here, same thing. We draw our alpha beta system, just take away the double bond because it goes away there, and then we add our amine to the beta position. With our sulfide, add it to the beta position. Neutral nucleophile providing its own acid as you add. So we make a thiol there, adds to the beta position. HBr, that proton there allows easy tautomerization back from the enolate. Add the bromide nucleophile to the beta position. Gilman reagent, same thing. We'll see the trend here. Add our carbon group to that beta position, ketone reforms. Okay, so let's talk a little bit more about enamines. So enamines are a good alternative to enolates. So they're softer nucleophiles and bases than enolates. And so we can carry out this beta addition in high yield, this 1,4 conjugate addition, in higher yield than we could with an enolate in much milder conditions. So it's safer, it's going to be more selective to the beta addition. All good things. Less reactive with other functional groups. So as we do that, just like the enolate, we form a CN double bond. Okay, and that alpha carbon attacks the beta here, conjugate addition, kicks up to an enolate. And the product of this is going to be a little bit squirrely to get a hold of, so we're going to be very careful in drawing these carbons that we've connected. So there are the 4 coming from the alpha beta system, and now we need this alpha carbon of the enamine to connect here to that beta position. And so then we need 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 carbons where our enamine was stuck here. And so forming that enamine, we required a secondary amine. So anytime we're forming an enamine over, this is a ketone, typically ketones work better for this. There are ways to make enamines from aldehydes. They involve other reagents like we'd form a Grignard reagent almost with magnesium bromide to help stabilize the enamine of the aldehyde. We're sticking with ketones and secondary amines for enamines for this as being the easiest to do. Other ways to do them, of course, but secondary amines always. Primary amines would make the imine. Okay, so we don't want to use a primary amine to make an enamine. Here with our enamine, they tend to go toward the kinetic side. So if we form an enamine like an enolate at -78, the alkylation tends to occur the less substituted side, presumably due to steric effects and kinetic control. Okay, even though it's a little less stable, it's going to be the position that gets alkylated more. All right, so we got that kinetic side when there's a choice there on the unsymmetrical ketone. Back to where we were, we've added to that alpha carbon, there it is, it's added to the beta position, or the 4 position of that alpha beta unsaturated system. What we're left over with, though, is an iminium ion that needs to be hydrolyzed, and we've got an enolate that needs to be protonated. So we'll follow up that enamine addition with a final step where we will where we will protonate with H3O+. It hydrolyzes the iminium and tautomerizes the enolate. And so if we draw our carbon backbone, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. At the 1, 2 position here, we've got our ketone that reforms from tautomerization. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That is where the other ketone forms after the hydrolysis of the iminium ion. And so look, you've separated 2 ketones by several carbons. So very powerful functionalization here as far as this goes. Now you do have potential of some intramolecular stuff here, and you will see that to a certain degree with the Robinson annulation. Okay, so stay tuned and check out the Robinson annulation mechanism for situations where this is a thermodynamic sink towards a cyclic product instead. And so you'll see that coming up. Another scenario where you've got this softer nucleophile is when you have a beta disubstituted system like a beta diketone. Okay, we need to be able to recognize these functional groups, understand that their pKa's are less than 14. Okay, so there's a high efficiency of proton transfer between hydroxide, whose conjugate acid pKa is 15.7, and that's so with a pK of about 9 to 10 for these beta diketones, you've got a pretty efficient transfer of about 10,000 to 1 or more in difference in equilibrium constants. So very high degree, 99.99% to the product. And what is that product? It is an enolate that forms from this acid-base reaction. We can show the alpha carbanion. We can show the enolate forming. To one side, we show the enolate forming to the other side. Overall, there's a resonance hybrid that stabilizes this enolate very strongly, and so it is a very soft nucleophile and a weak base. When we do the alkylation, however, we attack the beta position. This is called a Michael reaction. All of these beta additions are called Michael type reactions. They're more commonly seen with beta diesters, beta diketones to these alpha beta unsaturated ketones and aldehydes, but conjugate addition, Michael reaction tend to be synonymous. This is more closely related to some of the original reactions, and so as we look at this, we've got to keep track of everything again. And so we are going to form an enolate. Here are our 4 carbons of the alpha beta system. Here is our alpha carbon here on the di-substituted system. The more acidic protons are always in the middle between the 2 functional groups, not to the outside. And so as we connect to that alpha position, we end up with a diketone here. And we've got a pretty acidic proton right there, so you would actually get a rearrangement that would eventually put the enolate back into this position. But hydrolysis and acidification, just acidification and tautomerization will relieve that, and we end up with this triketone system. There are also equilibrium products that could result from intramolecular type reactions if the sterics allow it, but here we'd most likely end up with our system, because once you put the enolate back here, you'd have a hard time 1, 2, 3, 4 carbons making a 4-membered ring from an attack there. So we typically see this Michael addition end in this fashion. One more topic here, just as a point. Less active electrophiles, so electrophiles that are less active than unsaturated ketones and aldehydes. This is from our carboxylic acid derivatives. So esters, nitriles, and amides, tertiary amides, all of these being less active tend to favor conjugate addition. Okay, so we include them here. However, in practice, the regioselectivity and whether or not the reaction actually goes is highly specific to conditions and very specific catalysts that are used. Okay, so we'll assume for our purposes in class that these esters, unsaturated nitriles, unsaturated nitro groups, and so forth, nucleophiles are going to need to be stronger, and they're going to prefer to go towards that beta position in these situations where they are possible. We're not going to worry about those specific catalysts and conditions. It's beyond the scope of the class, so we just need to know that they do attach to the beta position when they go.